Hi. So in the last video I've made, I have shown you my register and how it works, and the 8-bit register and how it works and stuff. And I said that I'm going to be making it better this time around. So I did. I basically made it like 2 times smaller, and also made and also added a function and made it more efficient overall. So let's get into the explaining part. So my last my last I'm sorry. So my last design was something like this. It had 3 ICs over here on a single breadboard, then from an AND gate from 4069 integrated circuit. Yeah, this is how I'm going to be drawing into the integrated circuits. I'm sorry, I cannot draw very well, so yeah, you will have to get used to this. But from a 4069 there was going an output, and yeah, this was the set line going like this, and these were the input lines going like this, and they were connecting to their respective parts. And so I had this configuration 4 times because I could fit 2 bits on a single breadboard, like so. You can see the 2 bits in the 2 LEDs. I've also explained why I had to do it like this in my last video about like why did I have to connect the output through an NAT gate, or through any gate that is. And I chose a NAT gate so I could use only 3 chips per breadboard, which was still very inefficient. And this is why, because as you can see over here, I made a count for chips in my circuit, which was 16 AND gates, because 2 AND gates per bit, which is 8 bits, and it's 16 AND gates. Same with NOR gates, and same with NOT gates. But since the 4069 chip has 6 6 NOT gates per chip, I actually had 18, because I had 3 chips plus 4 NAND gates, which I used as NOT gates. So I had 22 NOT gates used in my circuit, as you can see here, and I needed only 16, which means there were 6 redundant gates. So yeah, in total I used something like 12 ICs or something, and 12 ICs, because 3 per breadboard, and I had 4 breadboards, and 54 gates. Yeah, so as you can see here, I used 2 NOT gates, 2 AND gates, and two NOR gates. And this chip has 4 AND gates, this chip has 4 NOR gates, and this chip has 6 NOT gates. And so I knew that this wasn't efficient. I also said it in my video, and I wanted to make it more efficient, more small, and use less gates, or use them more efficiently, that is, because I really needed like 2 NOT gate chips, but I used 4, well, 3 with the NAND gates. So I used way too many NOT gate chips, and I wasted a lot of gates. And I also lost one function, which was the read function from the circuit. I showed you the read function last time. It was like you can toggle a read so the register will output, but this one doesn't have it. This one only has set and input and output. It doesn't have any read, which the next design I have done does have. And it's pretty amazing of how I fit it, and I don't think I'll be able to make it smaller. But I sat on it for around like 2 hours or something. It took me a long time, and I've come up with the most optimal way of wiring the gates, in my opinion at least. If any one of you has an idea of how to make it more optimal, I'm open to ideas. So I mean, a person can learn like every day. So this is the new configuration I made. yeah, this is the new configuration. So as you can see here, this is a single breadboard. These 6 chips were fit on a single breadboard, and I have had fit them like this. So like for example, in this configuration, every single AND gate has uh, has a NOT gate which is like next to them. So yeah, as you can see, every single AND gate has a NOT chip right next to them, as you can see over here and over here, and yeah, here and here. So yeah, that is very efficient. And also this chip has only 4 outputs and this has 6 inputs, so it was more than enough. Yeah, it has 4 outputs and same as this one, but I didn't use all 4 outputs for this one. You'll see later why and how I used it, but it was basically used like differently. Okay, so it was more than enough. I actually had some redundant NOT gates over here, but it was less than these 6 redundant NOT gates, I'm sorry. And yeah, the same was over here. I had every single NAR gate had one AND gate basically next to it, and the AND gate was there for the read function. And these green lines, as you can see over here, are basically the lines that are the outputs of the circuit. Yeah, it's not done like this. It is going through a gate, and the gate it is going through is adding in a function. So yeah, let me show you how I did it. From my last video, you'll probably know that the NOT gate over here is basically inverting it. So yeah, this is the actual output, and yeah, as you can see, 3 AND gates per chip, only one NOT gate, and 2 NOR gates like usual. Yeah, but this AND gate is actually special because when I trigger it from this, it will enable the reading in the gate, which is super convenient for my usage because I can use this read function to work with it later, and I'm going to show you how I implemented it already. I'm sorry. And yeah, so when we go to the count of the gates, which is like over here, we'll see that there is 16 16 AND gates, and here is 24 because it's 8 times 3, which is 24. And yeah, but basically I used all the AND gates because I used all the AND gates over here, and I used, because there are 4 AND gates per chip, I used 2 chips which were 8 AND gates, which I needed for a configuration like this. And yeah, that's basically what I've done. Also, as you can see, I used 16 NOR gates, nothing changed there, but I only needed 8 NOT gates because I didn't use 2 per register, but I only used 1, which means I needed less, and then I needed basically, and then I used 12 because I couldn't use one integrated circuit. Yeah, I'm sorry, I couldn't use one integrated circuit per this 8-bit register, but I had to use 2 because I had 6 per circuit, but I only have yeah, I need 8, so I had to use one more, but that doesn't really matter since there were only 4 redundant gates in this entire circuit, and it added it a function, and it's basically all around better. It also used less gates because, as you can see over here, it used 54 over here and 52 over here. And yeah, as you can see, it is way more efficient. It is also space efficient because it's only on 2 breadboards, while I have it on 3 because I have the input module. Yeah, excuse me. So what I wanted to say is that this circuit is more efficient with gates. It uses less gate. It is smaller, so basically, and has one more function to it, which is useful. And so that's basically all the boxes I wanted to check, and I'm very happy with how it turned out to be. So yeah, I can now show you what it all done. Yeah, so it's basically just a better version, and what I wanted to do with the old one, yeah, I'm done with this one. And yeah, again, I don't think I'll be making it any better anytime soon. um so yeah, it's time to put my money where my mouth is, and here is the circuit. As you can see, it doesn't use two breadboards, it actually uses three, but this third one can be disconnected, and because it is basically only input and output, and it can be disconnected and something else can be hooked there, because yeah, for example, this wire, which is the right wire, is totally redundant, same with this read wire. These are the 8 inputs and these are the outputs. Yeah, as you can see, they are wired a lot neatly. Actually not neatly, neater, I'm sorry. Yeah, so when we compare it to the schematic I made, the very bad schematic, in fact, uh, yeah, we can actually see that this is the top board over here, and this is the bottom board over here, and this board isn't here because yeah, it, as I said, it can be replaced, and it really doesn't need to be there. In fact, yeah, so yeah, let's power it up and show how it works. I'm gonna take me a battery pack, which I have over here, and yeah, I can go and power it like this. Wait, is the voltage correct? Yep. Yeah, okay, so I have it powered, and you can see that nothing is actually shining. Wait, let me set it all to 0 and reset it, because as I said in my last video, it can be set off completely randomly. As you can see here, I didn't set anything into it prior, and it set this value, but it is random. So yeah, I reset it, and as you can see over here, this is the red wire, and this is the no, this is the read wire, sorry, and this is the right wire. These are pull down resistors, and yeah, these are the LEDs that are showing out the output. So yeah, let's input in some value. I don't know, something random, for example. Yeah, 1 1 0 1 1. Yeah, something like this. For example, when we read it, there is nothing over there, but when we reset it, yeah, it turns on. But when we disable the reading, it doesn't read from it, which is super handy for the application I'm going to be using it for. And yeah, as you can see, it works like a standard register. Wait, let me pull this onto an active high, so I do not have to hold the button. So now the AND gates are constantly powered in the output, so it is constantly reading. And yeah, I can show it to you that it in fact doesn't change. You only have to reset it, only then it changes. Yeah, it basically just functions like my old register, but it has this reading function, which is basically probably the biggest addition in my last circuit. And so yeah, I've basically saved this breadboard because I had only 4 now, but I'll be buying some more later. And yeah, so you can see that I can read from it, I can write to it. The output doesn't change when, excuse me again, so yeah, the output doesn't change. It basically a basic register. So yeah, I'm not now going to turn it off. I said I'm going to turn it off. So yeah, I'm going to reset it back to 0, and yeah, I'm going to be using this design because you can fit 9 integrated circuits that are DIP14, which means dual input package, which are basically these ones. I'm sorry. You can fit 9 of those onto one board, but I didn't fit 9, I fit 6, and they have such a nice configuration that I don't think fitting 9 onto one board will help me much. So yeah, I went with this one. So yeah, this is my new register design. I hope you liked it. Yeah, that's basically it. So yeah.